this video, I'm going to walk through some of the functionality of Pivot Interactives so that you can successfully complete the module activities as well as the more in-depth semester labs. Okay, so when we look at this, and this is the first module activity that you've interacted with, in the upper right there's this tools icon. That's going to be very important for every Pivot Interactive activity. So this is where your measurement tools will be found. And you're usually limited in what you have, just like you would be in a real life situation and in a real lab. You'd be provided with equipment and you need to figure out the best way to make some measurements. The other thing that you'll see is that we have a video of the motion. Now, these videos are sometimes provided by Pivot. Other times you will be uploading your own video and analyzing that motion. So one thing that you can do is you can press pause, and then after you press pause, you can use the bar at the bottom and adjust the motion, just as you would with a normal video. And then these buttons, the arrows to the left and right of the play button, advance it frame by frame. And so if we go to our tool, and we go to our timing tool, this is pretty much in every Pivot video we interact with, we can see that we're given the frames, but more importantly, we're given the time, the real time, the 0.2167 seconds here, for example. And as I advance it frame by frame, we can see that I'm then seeing the motion frame by frame and the time as well. So in this first one, you were just supposed to find the X and the Y velocity. And so the only other tool you were given is this grid spacing. You can see the grid has a grid spacing of 5 centimeters. And these tools can be moved, right? So you just drag them like you normally would. And so what you can do is decide what's the best way to use these tools. So these Pivot Interactive activities and labs are not made to sort of spoon feed you every single step. Just like in a real lab in person, you would need to decide what's the best way to make the measurement, what's the best way to use this tape measure or this ruler or this stopwatch. And that's exactly the functionality that you're going to interact with here. So you have this movable grid and you know that the spacing is 5 centimeters and you have the time. So if you need to measure the X component of the velocity, well, you can move this over. It's a constant velocity motion. So you can move this over, so say that a corner of it might line up with the center of the puck or some other definable feature on your object. And this is just, again, one option. And then I can go over to the timing, and if I press reset, it'll actually set that as my new t equals 0. So now I'm at t equals 0 at essentially my origin. And I just picked this random location in the video because it is constant velocity. And so then now I can actually just progress frame by frame, where I could drag the bar, and what I'm looking for is the horizontal velocity. So how long does it take it to go 5 centimeters in the horizontal direction? So I can get close, and then I can use the frame by frame adjustment to make fine details of that. And you can see then I'm getting that it's going to take just about 0.1542 seconds. And we deal with uncertainties in our actual labs, but for these basic functionalities, we'll just talk about, what you can do here. 0.1542 seconds for 5 centimeters in the X direction, because that's going to be how long it took to go 5 centimeters in the X direction. So that's going to give me my X velocity, my distance divided by time. Again, it's this constant velocity. So that's the X component of the velocity vector. If I wanted to do the Y velocity, I could go back to 0, or if I don't get it exactly, I could just reset a new time to 0. And now I'm going to be looking at the vertical motion. I want to know how long it takes it to go 5 centimeters in the vertical direction. And so again, I can advance frame by frame, and here in the vertical direction, I see it takes 0.1375 seconds to go 5 centimeters. So it's traveling a little bit more quickly in the Y direction. Now I chose to just look at 5 centimeters because this wasn't a lab with uncertainties. There wasn't multiple trials that you were doing. It was just for basic understanding of X and Y components of a velocity. I could, as best practice, maximize the grid that I'm given so that, for example, if I'm able to go 1, 2, 3, 4, 5, 6, so 6 times 5, 30 centimeters total in the Y direction, then I could figure out the total time to go 30 centimeters. So the longer measurements that you can make over the longer lengths For something like constant velocity, that would be better. But again, a lot of the choices are up to you as the user to make these decisions about what is best practices given the tools that you have. This exactly mimics what you would experience in a real life situation. And these are real life videos, so that as this goes, even though we say constant velocity, if you made measurements, you might have some slight fluctuations. It might slow down a little bit if it's not completely frictionless as this puck moves. And that's okay. There's not always one exact answer for labs or for real life measurements. So that would be how you would measure the velocity in the x and the y direction as a function of time in the first portion of this. And then you would have to enter your answers and continue. Then you could go ahead and you would have tested your prediction. Now here's an example of how you would be given different tools. You still have your timing tool, but now you're also given this very nice little protractor where the protractor it's shown where 50 centimeters is. So you made a prediction about how long it would take it to go 50 centimeters and what angle it'd be traveling at. So really at this point what you want to do is you would basically just wait until, and in this case some of your predictions might be slightly off if you didn't wait until the push was done. Again, we want to wait until the motion is constant, so it starts from rest and the person pushes it. So we wait till after the push is done, and then we can move our protractor. So then I can reset my time, and now I can advance my motion and figure out, okay, at what angle does it cross 50 centimeters? So what's the angle at which it's traveling at to check your previous prediction? And, at what time did it take it to go 50 centimeters? And you are going to have some small variations between your predictions and the actual values because these are real life measurements. And when we do our labs, our in-depth labs, you will start to think very carefully and critically about these uncertainties. Okay, so in the second portion of this video, I'm going to go ahead and we're going to just look at another one. And this is one that we're actually not going to interact with in a required way in this course, but it's kind of cool in that, again, just showing how we can make some measurements. That previous one had a grid. This one I'm showing because it has a couple features that you don't see in that first example. This one here, we have a rocket launch.
Main engine start, 0, and liftoff of the Atlas V with Curiosity.
And so you can actually see this is the Atlas V with Curiosity on it, and it's a real-life launch, so a real-life image of that launch. And what's really nice about this then is then they've gone and they've calibrated various rulers. So they have here 2 rulers, and you can see this one is black and this one is white, and that's just because sometimes it's easier, depending on the background that you're looking at, to see it in black or to see it in white. And so what you can do with this one is, again, if you pull up your timing tool, and these rulers are movable, and they're already calibrated for you when the video is provided. We'll get to how you calibrate your own ruler when you upload your own video. But you can see here that you can go to the very beginning of the motion when the rocket just starts to move. And then I can set that to 0 and then pick some sort of definable feature on the rocket, say this bar at the bottom. And now I would be able to advance frame by frame and actually get very detailed position as a function of time. And so what you can actually do is graph quite nicely the position as a function of time. And I also used this one because I can show you the some of the results of the sorts of things you might get here. So eventually we would be using their graphical tools. You can see the velocity as a function of time for the rocket. You could see the position as a function of time. In this case, horizontal axis would still be time, position as a function of time. And so it actually has a fairly constant acceleration for this motion. And so the velocity was calculated from the position versus time measurements, and there's data tables that get filled in. And that all comes from really just then again incrementing, reading the ruler and the time. So position is a function of time, just as you would in a real life scenario. In person-to-person labs, we often slow motion video our labs and use that video analysis. And so it is not actually very different using pivot than what we would do in an in-person scenario. Okay, and then lastly, I'm going to show us the second one that you're going to do. This is the actual second required one. And you can see here that this one also, again, has our common timing tool, has a ruler. And this is already calibrated for us as well. And this is the ping pong ball bazooka. And so this has here a very, very fast ping pong ball, slams into a Coke can, and then continues after that motion. So I want to pause it again, and that gives me the ability to control. And then I can go frame by frame. So after it's been shot from this bazooka, the ping pong ball travels with a constant velocity until it collides with the Coke can. And then after it collides, it'll travel again with a constant velocity, presumably slower, because it has given up some of its energy to the collision with the can. So in this case here, again, I would go ahead and pick some defining feature of the ball, and this doesn't have a circle in the middle. So sometimes what can be useful is they provide these little dots, and again, you can decide what's the best thing that you want to do with this dot. A lot of times I like to put it on the leading edge of the ball, and then I can say set this time to be 0. I can advance by 1 frame and take another dot. Oops, I moved my same dot, so I have to go back, and I'm going to move that dot there, and I guess what I will do is I will probably work backwards, where I will, because my dot, it looks like, will keep appearing at my initial stage. So if I then back up the ping pong ball, you can see how I had to be a little creative there so that I wasn't always, having to move the same dot or encounter the same problem. Just again, like you would in a regular lab environment, you have to kind of figure things out as you go. You have to think critically about what you're doing. So this is enough points here where I could really just say, okay, I want to call this 0. And so then now as it progresses through, I can see the time advance. I can move my ruler here. So I come back, I accidentally moved that dot. That will happen to you and you'll get used to it. I'm still learning some of it. So I come down here, and then I'm going to place my ruler, and now I actually just have these measurements as a function of time. So I can see where it starts for my t equals 0, how far it went again, and I can use those to get a pretty nice value for this initial velocity. I can then do the same thing after the collision. So after it has been done, and you can see the blur from it being such a high velocity. So what I can do then is, again, advance these through. And if I just go screenshot by, or frame by frame, the reason I'm doing this versus just making the measurements is sometimes these little dots right away show your expectations. So we can see here that these dots are closer together after the collision, meaning that before the collision, as I advance frame by frame, I have some higher velocity than I do after the collision, and that becomes immediately visible with those little red dots. So they're also very good for some conceptual understanding. Okay, so that hopefully gives you some introduction to what to expect from the basic measurement tools. There are some more advanced ones as we move along, but for the first few labs, this is the functionality for Pivot Interactives that you need to have. If you have any questions at all, please send me an email, sign up for an office hour time, or let me know.